Hi everyone, welcome to Go Classes. In this session, we will study functional completeness. We have already seen the definition of functional completeness and the concept of functional completeness we have already seen. Now we will continue that. So in this functional completeness, in this chapter, what we have seen so far? So far we have seen the definition and the idea of functional completeness, right? We have seen many examples and we have seen some guidelines to determine if a set of Boolean functions is functionally complete or not. Okay, so this is what we have seen so far. So we have seen some guidelines. I told you some guidelines to determine if a set of Boolean functions is functionally complete or not. A set of Boolean function will be given to you and they will ask you, is it functionally complete? Okay, so to check that, we have seen some guidelines. So this is what we have done so far. Yes or no? Now let's start and we will continue this functional completeness discussion. So let's start. Now you might be thinking, what is the source of these guidelines? I told you some guidelines to check if a set of functions, if a set of Boolean functions is functionally complete or not. You might be thinking that what is the source of these guidelines, from where these guidelines are coming? Yes or no? Are you curious? Please tell me. We have seen some guidelines and you might be thinking, what is the source of these guidelines? From where these guidelines are coming? Why these guidelines are correct? Okay, this is what you might be thinking. See what we have done. Let me tell you. So far, we have some guidelines we have seen to determine if a set of Boolean functions, will be given to you. If a set of Boolean function is functionally complete or not, for that we have seen some guidelines we have seen. Okay, so if X is a set of Boolean functions, for example, this X, this is set of Boolean functions like function f1, function f2, function f3, and so on, maybe function f4, like that. Okay, so this set will be given to you. This is set of Boolean functions. Now, this set of Boolean function, is this functionally complete or not? To check that, we have some guidelines. If you want to check it, then we have some guidelines. We have seen some guidelines. What are those? What are the guidelines? So if you have a set of functions, this is your set of functions, f1, f2, f3, something like that. Okay, so this is your set of functions. Now, if you want to find out this set X, this set of functions, is this functionally complete or not? Then for that, what you can do? What are the guidelines? The first guideline, what is that? Tell me, what are the guidelines? The first guideline is minimize every function. Yes or no? Minimize every fi. So this is what you do. Correct? Minimize fi. Minimize every function fi. Yes or no? So this is what you do. Then what is the second guideline? Please tell me. What is the second guideline? First you minimize this, minimize this, minimize this, minimize this, minimize this. First you minimize all these. Okay, minimize all of them. Then what is the second guideline? What is that? If for all of them, if you see, for all of them, if you replace all the variables by 0, if you are getting 0, means what I'm saying for all fi, I am saying that if you put 0, if you replace every variable by 0, for all fi, if you replace every variable by 0 and you get 0, let's assume, means if you replace every variable in f1 with 0, then you get 0. In f2 also, if you replace every variable by 0, you get 0. In f3 also, in f4 also. In all of them, remember, for all fi, if I replace all the variables by 0, then if you are getting 0, for all these functions, if you are getting 0, then what I can say? Then I can say this set X, this is not functionally complete. X is not functionally complete. Is this clear? This is your second guideline. What is the third one? What is the third guideline? Tell me. The third is for all fi. For all fi, if you replace all the variables by 1, for all fi, if you replace every variable by 1, then if you get 1, then what I can say? Then I can say that this X is not functionally complete. This set X, this is not functionally complete. This we have seen. What is the fourth guideline? Tell me. What the fourth one? Please tell me. So the fourth one is for all fi, if every fi is self-dual, for all fi, I'm saying, if every fi is self-dual, if every fi is self-dual, then what you can say? If that is self-dual, then what I can say? Then I can say X is not functionally complete. X is not functionally complete. Yes, correct. And what is the next one? What is the next guideline? Tell me. What was the next? The next one is if every function is linear, then I can say X is not functionally complete. Okay, for all Fi, I can say that if every function is linear, if Fi is a linear, if every function is linear, then what I can say? Then I can say that X is not functionally complete. Yes or no? Is this clear? So far, these are the guidelines that we have seen. Okay. And what is the sixth one? If none of these guidelines work, else I can say, else, remember, else what I can say? Else I can say, else I can this, else remember, else you have to create not comma or, okay. Or you can say else create not comma and. So this is the simple point. Else what you do? Else try to create, I can say not comma or. Else what you do? You try to create not comma or you try to create, or you try to create not comma and. So these things you try to create, or you try to create NAND, or you try to create NAND. Okay, or you try to create NOR, or you try to create NOR. So basically, try to create any of them. Try to create any of them. Is this clear? So these are the guidelines that we have seen. Is this clear so far? Please tell me. So these are the guidelines that we have seen. If a set of Boolean functions is given to you, and the question is, determine if this set of Boolean function X, if this X is functionally complete or not, then for that we have some guidelines. We have seen some guidelines. Okay. All these guidelines we have already seen. Now, you might be thinking, what are the source of these guidelines? From where these guidelines are coming? Yes or no? What are the source? So let me tell you the source of these guidelines, that is Emil Post's functional completeness theorem. So remember these guidelines, these are actually given by Emil Post. So Emil Post gave this functional completeness theorem, and from that theorem we have created these guidelines we have created. Okay. Now we will see this theorem, we will see in detail way. We will see this, but let me tell you the source of these guidelines, that is Post's functional completeness theorem. This is the source of these guidelines. Is this clear? Okay. So this is the source. So remember Emil Post created one theorem, gave one theorem, okay, to check functional completeness for a set of Boolean functions. If a set of Boolean functions is given to you, then to check whether this set of Boolean functions is functionally complete or not, Emil Post gave a theorem. Okay, this functional completeness theorem was given by Emil Post. Now let's see. In this theorem, you can see all these guidelines are actually given in this theorem. We will discuss this theorem in detail. Don't worry. We are going to discuss this theorem in a detailed way, but this is your post completeness theorem. Okay, it was given by Emil Post. Here you can notice. Okay, so let's discuss this in detail way. But I just want to tell you, all the guidelines that we have seen, these are standard. Okay, means these are coming from Emil Post functional completeness theorem. Now we will discuss this functional completeness theorem. This is what we are going to discuss. Okay, so let's start the discussion now. So now we will discuss this Post functional completeness theorem. One by one we are going to discuss. You can see there are 5 points. These 5 points we are going to discuss one by one. So let's start the discussion. So remember now these guidelines are not guidelines, these are actually theorem. Okay, so remember one thing. So far I was calling them guidelines. So far what I was calling them? I was calling them guidelines. Yes or no? So far I called them guidelines, but actually these guidelines are not guidelines, these are actually theorem. Now we will see the theorem. Okay, now what we are going to see? Now we are going to see the theorem. This theorem we are going to see. Okay, so now these guidelines will become a theorem. These will become a theorem. Theorem means these will become if and only if statement. These will become if and only if statement. Don't worry, I will explain, don't worry about it. But I am saying these will become if and only if statement. Means if this theorem works, I can say, if you satisfy this theorem, then the set will be functionally complete. If you don't satisfy, then it will not be functionally complete. So far I was calling them guidelines, but now I will call them theorem. Okay, this theorem we are going to study. Is this clear? So now we are going to study this theorem, post functional completeness theorem. This is what we are going to study now. So this theorem we are going to study. In this theorem, what is the input? In this theorem, what is the input? The input is a set of Boolean functions. This is the input. Okay, a set of Boolean functions is given to you. This is the input. And what is the question? The question is this set functionally complete or not? Okay, this is the question. A set of Boolean functions, this is the input. And the question is this set functionally complete or not? This is the question. So remember, your input is set of Boolean functions. Set X will be given to you, set of Boolean functions. So this X, this is set of Boolean functions, F1, F2, F3, and so on. F2, F3, F4, and so on. Okay, a set of Boolean functions will be given to you. And this is the question. This is the question. We have to find out. This is the question. Okay, so I can say this is the question. So very simple. Now let's see this theorem one by one, step by step. Let's see this theorem. So let's see the property 1 to check. If I give you a set of Boolean functions, remember, I will give you a set of Boolean functions. I will give you this set X. I will give you F1, F2, F3. This will be given to you. In the question, they will give you this set of Boolean functions. Now they will ask you, is this set X functionally complete or not? Then what the property 1 to check? Then what you will do? Then you will check property 1. And what is that? Tell me what is the property 1 to check? I told you. The property 1 you will check is, in this set, you will check if I replace every variable by 0, will I get 0 for all the functions or not? In this set is given to you. In this set, if I replace every variable by 0, okay, means for all fi, if I replace in every fi, if I replace all the variables by 0, if I get 0, then what I can say? Then I can say this X is not functionally complete. Then I can say this X is not functionally complete. Okay. Actually, let me tell you one thing. There is something called zero preserving function. Okay, let's see the definition of zero preserving function. What this property 1? Let me tell you. This property 1 is zero preserving function. Zero preserving function. Let's see the definition of zero preserving function. Zero preserving Boolean functions. What is a zero preserving Boolean function? What is that? The zero preserving Boolean function. The definition is like this. If I give you a function f, let's assume I give you a function f, a, b, c. I give you this function f. This is zero preserving. When I can say this is zero preserving? When I can say this is zero preserving? This function is zero preserving if and only if I replace all the variables by 0, then the function value is 0. Is this clear? See, very simple definition. Extremely simple definition. Please tell me, is this definition clear? When can I say a function is zero preserving? A function is zero preserving. When can you say a function is zero preserving? A function is zero preserving if and only if you replace all the variables by 0, the function value will be 0. Okay, if you replace all the variables by 0, then the function value will be 0. This type of function is called zero preserving function. Okay, this is called zero preserving Boolean function. Is this clear? So the definition is very simple. If I give you a function f, okay, if I give you a function f, let's assume this is your function f, then this is zero preserving. When can I say this is zero preserving? Tell me. This f, this is zero preserving if and only if you replace all the variables by 0, if you replace all the variables by 0, then the function value must be 0. Please tell me, did you understand this? Let me know. So this is the definition of zero preserving function. Okay. Now remember, if all the functions in X are zero preserving, then X is not functionally complete. Okay. Now this is a small result. I can say this is your result number 1. This is your result number 1. That if all functions in X, are zero preserving, if they are zero preserving, if all the functions are zero preserving, then X is not functionally complete. Is this clear? Please tell me. This was our guideline, if you remember. Okay. Now we are just calling it zero preserving. This definition I am giving you, but actually this guideline we have already seen. If you remember, this guideline we have already seen. Okay, so very simple point. If all the functions in this set X are zero preserving, then I can say this set X, this is not functionally complete. So this is the definition. So tell me, which of these functions is zero preserving? A question I'm asking, a very simple question. Which of the following functions are zero preserving? Some functions I am giving you, and you tell me which of the following functions are zero preserving. Are zero preserving. Remember, zero preserving means what? Zero preserving means, zero preserving simply means that this simply means that if you replace all the variables by zero, function value must be zero. Yes or no? If you replace all the variables by zero, then the function value must be zero. This is the definition of zero preserving. Now I am asking, which of the following functions are zero preserving? Some functions I am giving you. For example, let's take this function f a comma b. That is, for example, a or b. Let's see this function ab. Let's see this function a exclusive or b. Let's see this function a XNOR b. Let's see this function a implies b. Consider this function a bar. Consider this function a itself. Consider this function fab equal to 0. Fab equal to 0 means it is always 0. Okay, and no 9, that is fab equal to 1. So some functions are given to you. You can see OR, AND, XOR, XNOR. Okay, these functions are given to you. For example, what about NAND? What about NAND? This NAND, A NAND B. And what about NOR? A NOR B. So some functions are given to you. Tell me which of them are zero preserving functions. Let me know. Let me know which of them are zero preserving functions. See, this function is zero preserving, right? If you replace all the variables by zero, this will become zero. This is zero preserving. This is also zero preserving. This is also zero preserving. This is not zero preserving. Yes or no? The fourth one, that is not zero preserving. Because remember, see this XNOR. Look at this function fab equal to a XNOR b. Look at this function. If I replace every variable by zero, that means 0 XNOR 0, that is actually 1. Okay, so remember, this function is not zero preserving. This function is not zero preserving. Yes or no? This function is not zero preserving because if you replace all the variables by 0, you are not getting 0. You are not getting 0. Okay, what about the implication? What about the implication? What about this implication? This is also not zero preserving. This f a comma b. Look at this function a implies b. Okay, because if I replace all the variables by 0, then that will be 0 implies 0, and that is actually 1, which is not 0. So this is also not zero preserving. This function is also not zero preserving. Okay, this is also not zero preserving because you can see if I replace all the variables by 0, you are not getting 0. So this is also not zero preserving. Okay, what about this a bar? This is also not zero preserving. This is zero preserving. You can see f equal to a. This is zero preserving. What about this one? Tell me, what about this, which is always 0? This one, which is always 0. Yes. Okay, because this is also zero preserving. If I replace all the variables by 0, I will get 0. This is zero preserving. But this is not zero preserving, right? Yes or no? This is not zero preserving. Next, what about NAND? What about NAND? This is not zero preserving. What about NOR? This is not zero preserving. Yes or no? So this is the answer. Please tell me, did you understand? Let me know. So the answer is 1, 2, 3, 7, 8. 1, 2, 3, 7, 8. This is the answer. Okay, very simple. I hope you understood all these things. Please tell me, did you understand what the zero preserving that we have seen? If you replace all the variables by 0, then the result must be 0. This is the definition of zero preserving function. You can see this screenshot from a standard resource. You can see this. When can I say a function is zero preserving? When can I say a function is zero preserving? A function preserves 0 That means if you replace every variable by 0, the output must be 0. Okay, a function will preserve 0. A function is 0 preserving. If you replace all the variables by 0, the output must be 0. Very simple. Okay, so this is the idea. Now let's move on. Now let's see the second property to check. What the second property to check? Let's see the second property. This second property, if I give you a set of functions, then what the second property to check? That is one preserving. Okay, the second property to check, that is one preserving. That is one preserving. Let's see the definition of one preserving Boolean function. If you have a Boolean function, when can I say this is one preserving? What the definition of one preserving function? One preserving Boolean function. That simply means if you replace all the variables by 1, the result must be 1. Yes or no? So remember, if I give you a function, for example, if I give you this function, when can I say this is one preserving? When can I say this function is one preserving? Tell me. This function is one preserving if and only if I replace all the variables by 1, the output must be 1. The output must be 1. Okay, this is the definition of one preserving function. Very simple that if you have this function, let's assume this is your function. Now this function is one preserving. When can I say this function is one preserving? This function is one preserving if and only if you replace all the variables by 1, then output must be 1. This is the definition. Is this clear? Please tell me yes or no. Now what the result? What the result? Now this is your result number 2. What that? If all the functions are one preserving, then x is not functionally complete. If all functions in x, if all functions in x are one preserving, if all the functions in x are one preserving, if all of them are one preserving, then x is not functionally complete. Then x is not functionally complete. Okay, is this clear? If all the functions in x, I give you a set x, in this set x, if all the functions are one preserving, then x is not functionally complete. This is a result. Okay, don't worry, just keep watching. I will take a lot of questions. Right now we are just looking at some definitions. We have seen the definition of 0 preserving function. We have seen the definition of one preserving function. Yes or no? So right now we are just looking at some definitions. Then we will take a lot of questions, a lot of examples, all the GATE exam questions, everything we will do. Okay, so don't worry. So just understand the definition. What the definition of one preserving function? A function is one preserving. If you replace all the variables by 1, then the output must be 1. This is the definition. Okay, and if all the functions in this set x is given to you, this is the set of Boolean functions. In this x, if all the functions are one preserving, then x is not functionally complete. Okay, so tell me which functions are one preserving. Just tell me which functions are one preserving. Give me some functions, standard functions, which are one preserving functions. Tell me which are one preserving function and which are not one preserving function. Which functions are one preserving and which functions are not one preserving. Tell me which functions are one preserving functions and which functions are not one preserving functions. So let me know. So you can see that one preserving function, this AND is one preserving, yes or no? AND is one preserving, OR is one preserving. These are one preserving functions, yes or no? For example, exclusive NOR, this is also one preserving function. For example, this A itself, this is also one preserving function. Correct, yes or no? If I replace all the variables by 1, then this will become 1. So this is also one preserving function. What else? Let me know. Which else function? For example, I can say A implies B. This is one preserving function. These are one preserving functions. And what is not one preserving function? For example, XOR. XOR is not one preserving, right? Yes or no? XOR is not one preserving. See this XOR. Look at this XOR. This is not one preserving. Why? Tell me. This is not one preserving. Why? Because if you replace all the variables by 1, then the result is 0. The result is not 1. Okay, the result is not 1. Is this clear? This XNOR, this is your by implication. Remember, this XNOR itself is your by implication. This XNOR XNOR is your by implication. Okay, so this XNOR is same as by implication. Is same as your by implication. By implication. Okay, so remember, if I write like this, A XNOR B, that is same as A by implication B. Both are same. Okay, XNOR is same as your by implication. This is one preserving. Okay, what else? What about complement? What about not? What about A bar? This is not one preserving, right? Yes or no? What about NAND? NAND is not one preserving. What about NOR? NOR is not one preserving. So these are one preserving functions and these are not one preserving function. What about constant functions? What about constant functions? This is one preserving. This is not one preserving. Yes or no? These constant functions. Okay, this is one preserving. This is not one preserving. Is this clear? So this is the definition of one preserving function. Very simple. You can see this is the definition. Okay. If you replace all the input variables by 1, then the output must be 1. Okay. This type of functions are called one preserving Boolean functions. If you replace all the variables by 1, then the output must be 1. Okay. This type of function are called one preserving functions. Is this clear? Please tell me. Let me know. So simple idea. Okay. Now tell me one simple question I want to ask. If a function is zero preserving, can I say it is not one preserving? This is my question. If a function is zero preserving, can I say it is not one preserving? If a function is zero preserving, what you can say about it is one preserving or not? If a function is zero preserving, if a function f that is zero preserving, then what we can say about one preserving? Then what we can say about f being one preserving? Will it be one preserving or not? Please tell me. Will it be one preserving or not? Let me know. The answer, we cannot say anything. The answer, we cannot say anything. Yes or no? The answer is we cannot say anything. Is this clear? Remember, zero preserving function. See, what is a zero preserving function? If you have a function, notice. If you have a function, for example, A, B, C, if you want to check it is zero preserving, then which row of truth table you will check? Which row of truth table you will check? See, you will check this row if you want to check it is zero preserving or not. Okay. This row you will use to check zero preserving. Okay. This row you are going to use to check zero preserving. Okay. This row used to check zero preserving. To check if f is zero preserving or not. Yes or no? Is this clear? This row is used to check f is zero preserving or not. Okay. Very simple. And what about one preserving? This row is used to check f is one preserving or not. This row is used to check if f is one preserving or not. Okay. This row is used to check if f is one preserving or not. Okay. Is this clear? So give me a function which is both zero as well as one preserving function. Give me a function which is zero preserving also and one preserving also. Function which is zero preserving and one preserving Please tell me. Give me a function which is zero preserving and one preserving. What that function? For example, this function and this is zero preserving also, one preserving also. For example, this function, or for example, this f equal to a. So these are zero preserving also, one preserving also. Yes or no? Is this clear? These functions, these are zero preserving as well as one preserving. Okay. And what about this function, XOR? What about this function? Tell me. What about this function? This is zero preserving, but not one preserving. This is zero preserving. This is zero preserving, but not one preserving. Yes or no? But not one preserving. Is this clear? What about this XNOR? What this XNOR? This is not zero preserving, but this is actually one preserving. Correct? Is this clear? So very simple. And what about this? And what function is neither zero preserving nor one preserving? For example, look at NAND. For example, look at this NAND. This is neither zero preserving nor one preserving. Yes or no? So everything is possible. There is no relationship between zero preserving and one preserving. Is this clear? There is no relationship between zero preserving and one preserving. There is no relationship between them. Okay, is this clear? Please tell me. So absolutely no connection, no relationship between them. So remember, there is no relationship between zero preserving functions and one preserving functions. Zero preserving functions and one preserving functions. There is no relationship between them. Okay, there is no relationship between them. So simple point. Okay, let's move on now. Now let's see what is the third property to check. Tell me, what is the third property to check? That is self-dual. Yes or no? That is self-dual. So what is the property third? That is your self-dual. That is your self-dual. That you already know. That you already know what is a self-dual. So I can say, if all the functions in X is set of Boolean functions, remember, X is a set of Boolean functions. F1, F2, F3. So this X, this is set of Boolean functions, this X. Now I'm saying, if all functions are self-dual, then what I can say? This is the result number 3. What that? If all functions are self-dual, then X is not functionally complete. Yes or no? If all functions are self-dual, if all functions in X are self-dual, then X is not functionally complete. Yes or no? X is not functionally complete. And what is the definition of self-dual? Please tell me. What is the definition of self-dual function? Self-dual function means F is equal to F dual. Yes or no? Self-dual. That means function F is equal to F dual. This type of function is called self-dual. So tell me, which functions are self-dual, which functions are not self-dual? Among the standard functions, which are self-dual functions? Tell me, which functions are self-dual functions and which functions are not self-dual? Among all the standard functions, for example, you can see which function is not self-dual. Like I can say OR is not self-dual. Yes or no? The dual of OR, that is AND. Similarly, AND is not self-dual. Okay, yes or no? But you can see this A is self-dual, A bar is self-dual, 0 is not self-dual, 1 is not self-dual. Okay, what about exclusive OR? What about exclusive OR? That is not self-dual. The dual of XOR is XNOR. Similarly, this A XNOR B, this is also not self-dual. So these functions are not self-dual. Similarly, NAND, this is not self-dual. NOR, this is not self-dual. Okay, yes or no? Is this clear? Please tell me. Is there any confusion in this? We have already seen self-dual. A function is equal to its own dual. F is equal to F dual. This type of function are called self-dual functions. So you can see these functions are not self-dual. And these functions are self-dual. Yes or no? You can see not is self-dual. Because if I give you this F equal to, okay, consider this F equal to A bar. What is F dual? What is F dual? That will be A bar. So you can see F is equal to F dual. Yes or no? So this is the definition of self-dual. But if you notice, if I give you this function, A XOR B, then what is the dual of this? The dual of XOR is XNOR. So you can see G is not equal to G dual. So this is not self-dual. So this function is not self-dual. Okay. So very simple idea. Okay. So this concept of dual, this we have already seen in our lectures. Now let's move on. Now the next property to check, what is that? The property number 4 to check. What is that? Property number 4. This is linear. The property number 4 to check, that is linear. Linear function. Yes or no? A function is linear or not. This we have already seen. What is a linear function? This we have already seen, if you remember. Okay, in our lectures, we have already seen what is a linear function. Now you can see that in this set, remember this X is set of Boolean functions. This X is set of Boolean functions. This is your set of Boolean functions, F1, F2, F3, and so on. This is your set of Boolean functions. Now, if every function in this X is linear, then X is not functionally complete. Okay, this is your result number 4. What the result number 4? The result is if every function in X, if every function in X is a linear, if every function is linear, then X is not functionally complete. Okay, if every function in X is linear, then X is not functionally complete. Okay, then X is not functionally complete. Okay, so very simple this result. We have already seen what is a linear function. If you remember this definition, okay, did you watch the lecture linear function? When can we say a Boolean function is linear? Did you watch that lecture? Please tell me. Let me know. Did you watch it? When can I say a Boolean function is linear or not? Okay, so you can watch this lecture. This lecture I have already uploaded. You can watch this lecture. In this lecture, I have told you how to check if a function is linear or not. Okay, so this is the definition of linear function. You can check it out. When can I say a Boolean function is linear? A Boolean function is linear if either this happens or this happens. Okay, so this is the definition of linear function. Let me tell you what the definition of linear function. So you can see here, a function is linear if either this happens or this happens. And what it means? It means for every one value of f, the number of ones in the input are odd, and for every zero value of f, the number of ones in the input are even. So either this happens, or for every value of one, for every value of one of f, I can say the number of ones in the input are even, and the number of and for every zero value of f, the number of ones in the input are odd. So this is the definition. See what this definition is saying. Let me tell you. If you have a function f, this f is linear. What the definition? Let me tell you. This f is linear if and only if. When can I say this function f is a linear? Let's see this definition. See, this f is linear. Either this happens or this happens. One of them should happen. Either this should happen or this should happen. Okay, one of them should happen. Is this clear? Okay, so remember, when can I say this function is linear? This function will be linear. Either this happens or this happens. Okay, so what is that? Let me tell you. This f is linear if and only if, see, for whenever f is 1, okay, for all f equal to 1 rows, for all f equal to 1 rows, okay, whenever f is 1, then what should happen? For all, remember, for all f equal to 1 rows, number of ones should be, number of ones in the input should be even. Okay, number of ones in the input, number of ones in input should be even. Okay, and and whenever f is 0, and whenever f is 0, okay, and whenever f is 0, for all f equal to 0 rows, for all f equal to 0 rows, number of ones in the input should be odd. Number of ones in input is odd. Okay, so read this. This is the definition of linear function. Please read this definition. Very simple definition. F is linear if this happens. Okay, f is linear if this happens, or this happens. Okay, either this should happen or this should happen. So what I'm saying, f is linear if whenever f is 1, for all f equal to 1 rows, for all f equal to 1 rows, number of ones in the input should be even, and for all 0 rows, number of ones in the input should be odd. Okay, or what can happen, or it can happen that for all f equal to 1 rows, number of ones in the input should be odd. Number of ones in input, number of ones in input is odd, and for all 0 rows, and for all 0 rows, and for all f equal to 0 rows, for all f equal to 0 rows, number of ones in the input is even. Number of ones in input is even. Okay, so this is the definition. Please see this definition. Okay, this is the definition of linear function. This is the definition of linear function. Okay, either this should happen or this should happen. Okay, so when can I say a function is linear? If you want to check if a function is linear, just check, is this true or is this true? Means I am saying for all f equal to 1 rows, whenever f is equal to 1, in those rows, number of ones in the input should be even, and for all the f equal to 0 rows, number of ones in the input should be odd. Basically, number of ones you have to check in the input. Basically, number of ones in the input you have to check. Okay, similarly, for all f equal to 1 rows, number of ones in the input should be odd, and for all the f equal to 0 rows, number of ones in the input should be even. Okay, so this is the definition of linear function. This is the definition of linear function. Now, what the result? The result is, if every function is linear, then x is not functionally complete. Okay, this set x, this is set of Boolean functions. I am saying if every function in this x, means f1 is also linear, this is also linear, this is also linear. If every function is linear, then this set x, this set of Boolean functions is not functionally complete. Okay, is this clear? Now some student is asking, is it important to remember all these definitions? Yes, it is very important if you want to solve the questions based on functionally completeness. In the GATE exam, in GATE computer science, in GATE electronics, okay, in the GATE exam, in digital logic, functional completeness is an important topic. Okay, there are many questions in GATE computer science, in GATE electronics, there are many questions from functional completeness. Okay, and if you want to check whether a given set of functions, a set of functions will be given to you, whether a given set of Boolean functions is that functionally complete or not, then you have to apply this post functional completeness theorem. Okay, there is a theorem, there is a if and only if theorem, that is post functional completeness theorem. Okay, this theorem is there. We want to study this theorem, but before learning this theorem, before seeing this theorem, I am telling you all the important things, all the important definitions. Okay, so there is a theorem, post functional completeness theorem. There is a theorem. Before we see that theorem, okay, in that theorem, remember, in that theorem, we need to know what is linear function, what is zero preserving function, what is one preserving function, what is self-dual function. Okay, and one more, monotonic function. That is also coming. So these things we need to know. Okay, so we are looking at the definitions one by one. We have seen the definition of zero preserving function, we have seen the definition of one preserving function, we have seen the definition of self-dual function. Yes or no? Now this is your definition of linear function. This is the definition of linear function. Okay, now let's check which functions are linear, which functions are not linear. Okay, so tell me, what about f equal to a bar? What about f equal to a bar? Is this linear or not? Please tell me, is this linear or not? This function f equal to a bar, is this linear or not? Let me know. This function f equal to a bar, is this linear or not? Let me know. See, just create the truth table. Okay, just create the truth table. This is the truth table of f equal to a bar. Just create the truth table. Now if you look, okay, see, just apply the definition. Just apply the definition. Linear function means, you can see, whenever f is 1, in the input, how many ones are there? Whenever f is 1, see, for all rows, okay, for all rows where f equal to 1, for all f equal to 1 rows, tell me how many ones are there in the input? Tell me, for all f equal to 1 rows, how many ones are there in the input? How many ones are there in the input? This is the only row where f equal to 1 is there. Okay, how many ones are there in the input? There is 0, that is even. Yes or no? You can see number of ones in the input is number of ones in input, that is even. Input is even. Yes or no? Okay, is this clear? Now you tell me, if this happens, please tell me, if this happens, means for all the f equal to 1 rows, for all f equal to 1 rows, if this happens, that number of ones in the input is even, then for all the 0 rows, for all the f equal to 0 rows, number of ones in the input should be odd. Okay, so tell me, for all 0 rows, what is happening? For all f equal to 0 rows, tell me what is happening. For all f equal to 0 rows, let me know. How many ones are there in the input? How many ones? See, this is f equal to 0 row. How many ones are there in the input? There is odd number of ones. Yes or no? Odd number of ones in input. Number of ones in input is odd. Yes or no? Is this clear? So because this and this is happening, because these two things are happening, please understand, because these two things are happening, so I can say this f is linear. Yes or no? F is a linear. Is this clear? Please tell me. Because this is happening, this entire thing is happening. Is this clear? Please tell me. See, a function is linear if this happens or this happens. Yes or no? So here you can notice this is happening. This entire thing is happening. This entire thing is happening. Please tell me, is this clear? Let me know. Okay, so is this definition clear? Please read this definition. This is very important. F is linear. F is a linear. A function f is linear if this happens, or this happens, or this happens. Means for all f equal to 1 rows, number of ones in the input is even. For all f equal to 0 rows, number of ones in the input is odd. So either this should happen or. For all f equal to 1 rows, number of ones in the input is odd, and for all f equal to 0 rows, number of ones in the input is even. So either this should happen, this entire thing should happen, or this entire thing should happen. So here you can notice for this function f equal to a bar, for this function you can notice this is happening. Okay, for f equal to a bar, this is true, this is true. So function is linear. Is this clear? Please tell me. So f is linear. Okay, let me know. Understood? What about f equal to a and b? What about this one? What about f equal to a and b? Just create the truth table and check. What about f equal to a and b? 0, 0, 0, 1, 1, 0, 1, 1. What about this one? Please tell me. F equal to a and b. This is your truth table. For all f equal to 1 rows, what is happening? See, here you notice. For all f equal to 1 rows, what is happening? Let me know. For all f equal to 1 rows, this is f equal to 1 row. For all f equal to 1 rows, what is happening? Let me know. How many ones are there in the input? How many ones in the input? Even number of ones. Yes or no? Even number of ones in input. So what should happen? So what should happen? Please tell me. So what should happen? So what should happen? So for f equal to 0, what should happen? For all f equal to 0, what should happen? F equal to 0 rows, what should happen? F equal to 0 rows, what should happen? You must have odd number of ones. Is it happening? For all f equal to 0 rows, for all f equal to 0 rows, are you getting odd number of ones in the input? Are you getting odd number of ones in input? Are you getting for all f equal to 0 rows? Look at all the f equal to 0 rows. Are you getting odd number of ones in the input? Are you getting odd number of ones in the input? No. Sometimes you are getting odd number of ones, sometimes you are getting even number of ones. Look at this. Look at this. Sometimes you are getting odd number of ones in the input. Sometimes you are getting even number of ones in the input. Okay, yes or no? So you can see. So this is not happening. Yes or no? This is not happening. So finally, what I can say, please tell me. So you can see this thing is false. So you can see this thing is false. Okay, this thing is false. Yes or no? So I can say this function is not linear. Is this clear? Please tell me. Let me know. So you can see this thing is false. This thing is false. So I can say this function is not linear. So this AB is not linear. Did you understand? Please tell me. Not linear. The definition, did you understand? Let me know. The definition, did you understand? So this f equal to AB, that is not linear. That is not linear. Okay. So please understand the definition. You can see here in this function, you can notice f equal to AB. In this function, you can see that for all f equal to 1 rows, for all f equal to 1 rows, you can see this is f equal to 1 row. For this row, you can see number of ones in the input is even. So for all the 0 rows, number of ones in the input should be odd. But you can notice in this row, you are getting even number of ones in the input. Okay, for this row, you are getting odd number of ones in the input. So I can say this function AB is not linear. What about A or B? What about this function A or B? Please tell me. What about this function A or B? Let me know. What about this function A or B? 0, 0, 0, 1, 1, 0, 1, 1. This is your function. What about this function? See, can you notice? Whenever f is 1, sometimes you are getting odd number of ones in the input, sometimes you are getting even number of ones in the input. So the condition cannot satisfy, yes or no? Is this clear? See, can you notice? For all f equal to 1 rows, for f equal to 1 rows, if you notice one thing, for all f equal to 1 rows, if you notice one thing, neither you are getting input having even number of ones, neither you have even number of ones, even ones in input, yes or no? Nor you have odd number of ones in the input. Is this clear? Okay, so you can see that condition is not satisfied. Is this clear? Please tell me. See, whenever function is 1, for all f equal to 1 rows, for all f equal to 1 rows, whenever f is 1, sometimes in the input you have odd number of ones, sometimes in the input you have odd number of ones, sometimes in the input you have even number of ones. Yes or no? Sometimes you have odd number of ones in the input, sometimes you have even number of ones in the input. So what I can say? I can say that condition, the definition of linear function, that is not satisfied. So I can say this is not linear. This function is not linear. Is this clear? Please tell me. Let me know. Is this understood? Okay. So if you check, just look at the definition of linear function. The definition of linear function is not satisfied. Just look at the definition of linear function, that is not satisfied. Is this clear? Please tell me. Let me know. The definition of linear function, is that clear? Now let's see. What about exclusive OR? What about A XOR B? What about that? Please tell me. What about A XOR B? 0, 0, 0, 1, 1, 0, 1, 1. This A XOR B. What about this one? What about this one? Yes, this is linear. Why this is linear? See, this is linear because what is happening? See, for all f equal to 1 rows, for all f equal to 1 rows, what? How many ones are there in the input? How many ones are there in the input? How many ones? Odd ones in the input. Odd ones in input. Okay, yes or no? Odd ones in the input. In the input, you have odd number of ones. And for all f equal to 0 rows, what is happening? How many ones in the input? How many ones in the input? You have even number of ones in the input. Yes or no? Even number of ones in the input. Okay, yes. So I can say this is linear. This is linear because you can notice for all f equal to 1 rows, odd number of ones in the input. For all f equal to 0 rows, even number of ones in the input. Okay, so that is the reason. Because this is satisfied. Because this is satisfied. So I can say this XOR is a linear. XOR is linear. Okay, is this clear? What about XNOR? What about exclusive NOR? Please tell me, what about exclusive NOR? If I ask you, what about XNOR? Let me ask you, XNOR. A XNOR B. Please tell me. This is the truth table of XNOR. Now you can notice, whenever f is 1, you have even number of ones in the input. Yes or no? Whenever f is 1, you have even number of ones in the input. And whenever f is 0, you have odd number of ones in the input. Is this clear? So again, that is linear. Again, this XNOR is also linear. This is also linear. Okay, understood? Please tell me. What about implication? What about A implies B? What about implication? Please tell me. What about this implication? 0, 0, 0, 1, 1, 0, 1, 1. What about this implication? See, this is the truth table of implication. This is the truth table of implication. Now again, you can notice for all f equal to 0 rows. See, whenever f equal to 1 rows, look at f equal to 1 rows. Look at f equal to 1 rows. Sometimes you have even number of ones in the input. Sometimes even ones in the input. Yes or no? Sometimes you have even number of ones in the input. Sometimes odd number of ones in the input. Sometimes odd ones in the input. Correct? See, sometimes you have even number of ones in the input. Notice. Okay. For example, you can see here you have even number of ones in the input. Here you have even number of ones in the input. Okay. So you can see. Okay. Even number of ones in the input. For example, here even number of ones in the input. But you can notice here you have odd number of ones in the input. Yes or no? So this function is not linear. This function not linear. Please tell me, understood? This function is not linear. I hope you understood the definition of linear function. Is this clear? Let me know. So far, everything that we have seen. Similarly, you can see NOR. What about NAND NOR? What about NAND comma NOR? What about NAND? Look at this NAND. This is NAND. NAND means and negation. Okay, that is your NAND. So if you look at this NAND, then what will be your truth table? The truth table will be, this will be the truth table. Now you can easily see again for all f equal to 1 rows. Look at that. Look at f equal to 1 rows. Look at f equal to 1 rows. Sometimes even ones in the input. Sometimes you have even ones in input. Okay. And sometimes you have odd number of ones in the input. And sometimes odd ones in the input. Odd ones in input. Okay. Yes or no? Is this clear? For example, here you can notice even ones. In the input, you have even number of ones. Here you can notice you have odd number of ones in the input. Okay. So this is also not linear. This function is also, remember, this function is also not linear. What about NOR? What about A NOR B? What about that? Please tell me. I am asking what about NOR? A NOR B. What about that? A NOR B. That means negation of OR. Negation of OR. Okay. So if you look at the truth table, what will be the truth table of NOR? 0, 0, 1, 0. Okay. So let's see what the truth table of NOR. The truth table of NOR will be, that will be 1, 0, 0, 0. Yes or no? This will be the truth table of NOR. Now you tell me. Now you can see. See, whenever f is 1, whenever f is 1, how many ones in the input? Whenever f is 1, whenever f is 1, you have even ones in input. Yes or no? Even ones in input. Correct. Okay. Then what should happen? If this happens, whenever f is 1, whenever f is 1, you have even ones in the input. In the input, you have even number of ones. See, in the input, there is no 1. That means 0, 1. 0, 1 means even number of ones. So I can say whenever f is 1, you have even number of ones in the input. Then this should happen. This must happen where f equal to 0 rows. Okay. For all f equal to 0 rows, what should happen? Please tell me. For all f equal to 0 rows, what must happen? You must have odd number of ones in input. You must have odd number of ones in input. Are you having odd number of ones in the input? Are you having odd number of ones in the input? Whenever f is 0, you must have odd number of ones in the input. You must have odd number of ones in the input. Okay, whenever f is 0, whenever f is 0, you must have odd number of ones in the input. But you can notice that is not happening here. See here, look at here. F is 0, but you don't have odd number of ones in the input. Okay, so again, this is not linear. Is this clear? Okay, so you can see. Okay, so that is the reason I can say this function is not linear. I hope you understood. Please tell me, did you understand the definition of linear function? Did you understand? See, we have already seen this. What is a linear function? What is not a linear function? This we have already seen. You can watch that video also. Okay. Again, I have repeated the entire concept. I have told you the definition of linear function. I have taken all the examples, all the questions I have taken. Okay. But this concept, linear Boolean function, this concept we have already seen. I have already uploaded one video on this concept, linear Boolean function. Okay, so you can watch that video also. But I have again told you what is a linear function. Is this clear? Please tell me. So did you understand what is a linear function? What is not a linear function? Please tell me. What is a linear function? What is not a linear function? Did you understand that? Okay. We will revisit this linear function. There are some points that I did not tell you. I will tell you when we revisit. Okay. We will revisit this linear function. Is this clear? This topic, linear function, we will revisit. Okay. But before that, let's see the next property. That is property number 5. Okay. So let's see. This is the last property. This is the final property. I told you this Post, Emil Post. Emil Post gave 5 properties. Okay. So this is the last property we need to see. That is property number 5. Okay. So let's see what is this property number 5. This is monotonic property. This is monotonic property. This is monotonic property. What is this monotonic property? See, this is interesting. Okay, so please try to understand. This is quite simple. We will see how to check whether a Boolean function is monotonic Boolean function or not. So let's see the definition of monotonic Boolean function. Monotonic Boolean function. Okay. This monotonic Boolean function. See, this definition I will tell you. Okay, don't worry about the definition right now. Don't worry about the definition. What the definition of monotonic Boolean function? Don't worry about it. But let's directly see the result. The result number 5. What that? If all the functions are monotonic, then this set X, this is not functionally complete. See, this is your set of Boolean functions. Yes or no? This is your set of Boolean function. This X, this is a set of Boolean functions. Now the result, what is the result number 5? The result number 5 is this, that if all functions in X, if all functions in X are monotonic, if all functions are monotonic, okay, if all functions in X are monotonic, then X is not functionally complete. Then X is not functionally complete. So this is the theorem. Now you might be thinking, what is the definition of monotonic Boolean function? When can I say a Boolean function is monotonic? When can I say a Boolean function is not monotonic? Don't worry about it. I will tell you. Okay, after some time, I will tell you. Now let's move on. Now let's see the final theorem. Okay, so far all the concepts that we have seen, now we are going to use them. Okay, so far, tell me what we have seen so far. Can you tell me? Can you tell me? So far we have seen the definition of when can I say a Boolean function is 1 preserving, 0 preserving. See, we have seen so far, we have seen Boolean function. When can I say a Boolean function is 1 preserving, 0 preserving? This definition we have seen. When can I say a Boolean function is 0 preserving? We have seen when can I say a function is 1 preserving? Okay. Is this clear? We have seen when can I say a Boolean function is self-dual. We have seen when can I say a function is linear, a Boolean function is linear. And the fifth property was monotone. Yes or no? And the fifth property was monotonic. Okay. So remember, when can I say a Boolean function is, if you have a Boolean function, when can I say it is 0 preserving? When can I say it is 1 preserving? When can I say it is self-dual? What is linear Boolean function? And the last property, that is monotonic Boolean function. Yes or no? So these 5 properties, from these 5 properties, you can create a theorem. Emil Post, okay, as I told you, Emil Post created a theorem. So this is, I can say this is a theorem by Emil Post. What this Emil Post said, let me tell you. Okay, so understand the theorem of Emil Post. This is very important and very nice theorem. Let me tell you, this is a very nice theorem. what this Emil Post theorem. Okay, so now let's see Emil Post theorem. Emil Post functional completeness theorem. Functional completeness theorem. Okay, what this theorem says. This is very interesting theorem. First of all, what the input of this theorem? Let me tell you. What they will give you. What they will give you. In the question, they will give you a set of functions. Okay, a set of Boolean functions will be given to you. F1, F2, F3, F4, something like this. Okay, so a set of Boolean functions. So the input is basically set of Boolean functions. Okay, a set of Boolean functions, that is the input. Okay, this is the input. Now, what the question? What is the question? What the question to answer? Which question we want to answer? What is the question we want to answer? The question to answer is this set of functions means this x is functionally complete or not? X is functionally complete or not? Is this clear? This is the question that we want to answer, whether this x is functionally complete or not. Okay. Now, what this Emil Post said, what this theorem? This theorem is very interesting, let me tell you. This theorem says that this x is not functionally complete if any one of them will happen. See, this, okay, this x is not functionally complete if and only if x is not functionally complete. X is not functionally complete if and only if any one of them happens. Okay, see, x is not functionally complete. X is not functionally complete if and only if. This is if and only if theorem. This is if and only if theorem. Okay, so remember, x is not functionally complete if and only if either this happens. What happens? Either this happens that all fi are zero preserving. All fi are zero preserving. Okay, means if all the fi, if all these functions are zero preserving, if all of them are zero preserving, then I can say x is not functionally complete. Or, okay, or if all fi are one preserving, okay, all fi are one preserving, if this happens, then also I can say that this x is not functionally complete. Is this clear? Or what the next part? Tell me. The third one, that is all fi are self-dual. Okay, if all fi are self-dual, then also x is not functionally complete. Or if all fi are linear, if all fi are linear, then also it is not functionally complete. Okay, and finally the fifth point. Finally, the fifth point, if all fi are monotonic. If all fi are monotonic. Okay, so these are the 5 points. Is this clear? Please tell me. Please let me know. Is this clear? Okay. So this is the point. I hope you understood. So remember, there are five points. If all functions are zero preserving, you can say x is not functionally complete. If all are one preserving, you can say x is not functionally complete. If all are self-dual, you can say it is not functionally complete. If all are linear, you can say it is not functionally complete. If all are monotonic, you can say it is not functionally complete. So when it will be functionally complete, tell me. Now tell me when it will be functionally complete. X is a functionally complete if and only if. Now tell me, when can I say this is functionally complete? See, some student is asking, can I say Post theorem is negativity test? No, this is if and only if theorem. This is if and only if theorem. Okay, this is both ways, two ways. This is positivity test also, negativity test also. This is if and only if theorem. So tell me, when can I say x is functionally complete? Let me know. When can I say x is functionally complete? So x is functionally complete if and only if at least one function should be not zero preserving. Yes or no? I can say at least one of them is not zero preserving. Is not zero preserving. Yes or no? At least one of them should be not zero preserving. Because if all are zero preserving, then x is not functionally complete. Please understand. If all are zero preserving, all of them are zero preserving, then X is not functionally complete. So I can say, if you want X to be functionally complete, if you want this to be functionally complete, then at least one of them should be not zero preserving. Is this clear? Should be not zero preserving. At least one of them should be not zero preserving, and and at least one of them should be not one preserving. Yes or no? And at least one of them is not one preserving. Not one preserving. And what should happen? See, notice, if all of them are one preserving, then what will happen? Please tell me. Simple question I'm asking. If all of them are one preserving, then X is not functionally complete. Yes or no? If all are one preserving, then X is not functionally complete. So I can say at least one of them should be zero preserving, at least one of them should be one preserving, and at least one of them should be, and tell me, at least one of them should be, at least one of them, at least one of Fi is not self-dual, is not self-dual. At least one of them is not self-dual. And tell me, and at least one of them, and at least one of them, at least one of Fi is not linear, is not linear, and at least one of them is not monotonic. Okay, and at least one of them is not monotonic. At least one of Fi is not monotonic, is not monotonic. Okay, understood? Is this clear? Okay, so let me write it in just one line. In one line, let me write it. In one image, in one page, let me write it. So you have a set X. This is your given set X. This is the given set of Boolean functions. A set of Boolean functions is given to you, F1, F2, F3, and so on. This is the set of Boolean functions. Okay. Now I can say this X is functionally complete if and only if X is functionally complete. When can I say X is functionally complete? If and only if. Okay, X is functionally complete if and only if at least one of Fi, at least one of Fi, okay, at least one of Fi is, okay, see, remember, at least one of Fi is, I can say here, at least one of Fi is not, okay, now you can see, so this will happen. At least one of Fi is not one preserving, is not zero preserving, is not one preserving. Similarly, at least one of Fi is not self-dual. Okay, at least one of them is not linear, and at least one of them is not monotone. Please tell me, did you understand? Let me know. Did you understand this theorem? What this theorem is saying? Did you understand the statement? Don't worry, we will do a lot of practice. Don't worry, we will do a lot of practice. We will do a lot of practice. But did you understand the theorem? The theorem is very simple. See, read this. A set of functions is given to you. A set of Boolean functions is given to you. When can I say this X is functionally complete? This X is functionally complete if and only if. This is if and only if theorem. This is if and only if theorem. Okay, remember, this is if and only if theorem. Okay, if and only if at least one of them is not zero preserving, at least one of them is not one preserving, at least one of them is not self-dual, at least one of them is not linear, at least one of them is not monotonic. Is this clear? Please tell me. Let me know. Is this clear? And the same thing I can say for not functionally complete. Okay, given X is a set of Boolean functions. X is set of Boolean functions. So given this X, when can I say X is not functionally complete? Tell me. When can I say X is not functionally complete? If and only if. When can I say X is not functionally complete? If and only if all Fi, okay, all Fi are zero preserving, all Fi are zero preserving, all fi are zero preserving, or okay, there is or here, or all fi are one preserving, all fi are one preserving, or 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 all fi are self dual, or all fi are monotonic. Okay, I can say or all fi are linear, and finally or all fi are monotonic. Okay, all fi are monotonic. That's it. So please tell me, understood? See, is this clear? So if you want to say it is not functionally complete, then what I can say? X is not functionally complete if all of them are zero preserving, or all of them are one preserving, or all of them are self-dual, or all of them are linear, or all of them are monotonic. Okay, similarly, when can I say X is functionally complete? When can I say this set of Boolean functions is functionally complete? This will be functionally complete if at least one of them is not zero preserving, at least one of them is not one preserving, and at least one of them is not self-dual, and at least one of them is not linear, and at least one of them is not monotonic. This is the theorem. You can see this is the complete theorem. At least one of them is not zero preserving, at least one of them is not one preserving, at least one of them is not linear, at least one of them is not monotonic, at least one of them is not self-dual. You can see this statement. This screenshot is taken from a standard resource, and this is taken from Post original paper. Okay, this screenshot, you can see this screenshot. There are 5 classes. Yes, there are 5 classes. As I told you, there are 5 classes. There are 5 classes. Okay, so this is your post functional completeness theorem. You can see this. I hope you understood the statement of post functional completeness theorem. Did you understand? Please tell me. So far, everything that we have seen, did you understand? Now we will take a lot of questions, a lot of examples we will take. But before that, I want to ask you, so far, whatever we have seen, did you understand? Please tell me.